Hello. This is the first of the 3 sessions on projectile motion. Links to the other 2 sessions are placed below. In this first session, we will talk about the basics of 1D projectile motion. Session 2 will move on to 2D basics, and in the third session we will cover some more interesting and challenging projectile motion problems that typically would not be covered in high school or college physics, but I believe would enhance our understanding of the topic. Projectile motion. First is the motion. Motion is associated with position, time, velocity, and acceleration. A projectile is an object, once thrown out, or projected, does not have any further means to propel or control its trajectory. A rock thrown is a projectile. So is a baseball pitched. Or a cannonball fired. A rocket launched, on the other hand, is not a projectile, as a rocket after launch can further propel itself and even change the direction it's traveling. In short, projectile motion is the study of position, time, velocity, acceleration of a projected object with no further means of propelling or controlling its trajectory. There are outside or external forces that can act upon a projectile, such as gravity and air resistance. Most of the time, the force of gravity is assumed constant, and the air resistance is neglected, all to simplify the mathematical calculations. This is fine for entry-level learning, and the approximation is often quite accurate. However, as explained 1-2-3 always likes to do, we will delve a bit deeper in the third session to explore some fun situations where these often neglected terms do play a significant role. But for now, we assume constant gravity and no air resistance. Since gravity is the only force and g is constant, velocity, or v, is simply the starting value, v sub 0, plus the contribution from gravity. Okay, let's take a look at a simple case where a rock is tossed straight up in the air, and let's look at a bit closer how the rock travels. We first put up a vertical scale, call it y-axis, with up being positive and down negative. Y sub 0 is the starting position, and a rock will go up and up, till reaches maximum height, y sub max, and then falling down. We know acceleration is the change of velocity, and in this case, it's negative 1g, because gravity is point downwards, and it's constant. Remember, we define up as positive and down as negative. So, the velocity in the y direction, v sub y, is just the initial velocity v sub 0 y, minus g times t. The y position is the starting position, y sub 0, plus velocity, v sub y, times time t. But, since v sub y changes over time t, we need to do an integration here. If it's constant, just simply multiply by time t. Since it's changing over time, we do an integral over time. Substitute in v sub y, and a rather easy integral, just using the calculus, we have y equals initial position y sub 0, plus initial velocity v sub 0 y times t, and minus 1/2 of g times square of time t. There you have it. These are the 2 basic guiding equations of 1D projectile motion, and you understand why they are what they are, and where they come from, or how they are derived. Indeed, we can use these 2 basic and simple equations to solve all the 1D vertical projectile motion problems. So, let's get rid of everything else, and just keep these 2 equations. Move them up there. Throw in a stick man me, holding a rock in my hand, well, let's say it's a ball rather, so I don't get hit by the rock or anything. We also include a vertical scale like we did before. And then I toss the ball vertically straight up like so. The ball will go up and up, reaching the maximum height, y sub max, and then start falling, eventually hitting the ground. Suppose I release the ball 1 meter off the ground at a speed of 8 meters per second, and let's see what happens. Let's leave the ball positions in midair so it's easy to see. At a small time increment later, 0.2 seconds later, we have the velocity, v sub y, equals 8 meters per second minus 10 meters per second squared times 0.2 seconds. And that comes to 6 meters per second. This is just by using the first equation up there for velocity. Very simple. And note that we approximate the gravity to 10 meters per second squared, just to simplify the calculation. 9.8 is the actual g, but 10 is close enough for our demonstration here. And for position, we have y equals 1 meter, that is the initial position where I released the ball, plus 8 meters per second times 0.2 seconds, minus 1/2 times 10 meters per second squared, times 0.2 seconds squared. It comes to about 2.4 meters, and that was by using the second equation up there. As you can see, we can repeat the exercise and calculate for velocity and position for any given time. So, we did that, and put them in a table like so. Very nice. But, wait a minute, what about the very bottom row in this table? This is when the ball hits the ground, we know that, because y equals 0. How do we find out the time, t, and velocity, v sub y, when that happens? In this case, we know the final position of the ball when it hits the ground, that is, y equals 0. And we want to solve for time and velocity. We start with the right-hand side equation. We have the initial and final position, and we know the initial velocity, so we can solve for time, t. Simplify the equation, and the only unknown is t. We know how to solve this, and the solution comes to 1.72 seconds. Once we know the time when the ball hits the ground, we can then use the left-hand side equation to solve for the final velocity when the ball hits the ground. And that comes to 9.2 meters per second, pointing downward because of the negative sign. There you have it. Now we have a fully completed table. Nice. Let's look at the table a bit closer. One thing we see very interesting is that when the ball was first tossed up at 1 meter from ground, the velocity is 8 meters per second pointing upward. When the ball, after went up, returned to the same starting position, 1 meter from the ground, the velocity is also 8 meters per second, except it's point downward this time. Wow. That's interesting. Coincident? Actually not. This is a good segue to our final bonus topic, an alternative method by using conservation of energy. If you are familiar with mechanical energy, you know 1/2 mv squared for kinetic energy, and mgh for potential energy, or PE, where m is the mass of the object. The law of conservation energy states that the total energy, Ke plus PE, must stay constant when there's no work done. And remember we assumed no air resistance, hence no work. When the ball leaves my hand at time of 0, and when it returns to that initial position of 1 meter off ground, potential energy is the same, both are 1 meter from the ground, therefore the kinetic energy must also be the same. Hence, v squared must be the same. Going up or going down doesn't really matter as 1/2 mv squared is the same. We can also use this conservation of energy to solve the previous problem of what the velocity is when the ball hits the ground. I don't know about you, but I find this method is much easier. All we need to do is have the total energy, or Ke plus PE, remain constant. In this example, we find Ke plus PE at y of 1 meter, and then again at y of 0 meter when the ball hits the ground, and we can get the velocity, v sub ground, directly in a single step. It comes to 9.2 meters per second, and we know that it has to be negative because the ball is going downward. We can also put this in a more general form, and you can find answer to any two positions like so, as long as there's no external work involved, in our case, no air resistance. That's all for now. And if you like what you see, please hit the like button, subscribe, and share. Thank you.